Boolean expression derivation. The Boolean expression for the full adder output are derived systematically from the truth table using some product methodology. For the carryout expression, we identify all row where Cout equal 1 and write the corresponding min term. This yields Cout equal a bar dot b dot c in plus a dot b bar dot c in plus a dot b dot c in bar plus a dot b dot c in. Applying Boolean algebra simplification, we factor out common terms. From the expression, we can extract C in times the quantity A bar dot B plus A dot B. We simplify to C in times A exclusive of B. We also factor out A dot B from appropriate term. This yields the simplified expression Cout equal A dot B plus C in times the quantity A exclusive of B. For the sum output, following similar analysis of the truth table, we obtain sum equal A bar dot B dot C in plus A dot B bar dot C in plus A dot B dot C in bar plus A bar dot B bar dot C in. Through algebraic manipulation, this expression simplified elegantly to sum equal A exclusive or B exclusive or C in. This final form revealed that the sum output can be generated by cascading two exclusive or operation, which has important implication for circuit implementation efficiency. Logic circuit implementation. The full adder logic circuit demonstrates the physical realization of the simplified Boolean expression. The implementation consists of two distinct functional parts. For the sum output shown in the upper portion of the circuit highlighted in purple, input A and B are first processes through an exclusive OR gate, generating the intermediate signal A exclusive OR B. This intermediate result is then combined with the carry-in signal through a second exclusive OR gate, producing the final sum output equal to A exclusive OR B exclusive OR C in, exactly matching our derived expression. For the carry-out output shown in the lower portion, the circuit employs three gates. The intermediate signal A exclusive OR B is combined with C in through an AND gate, producing the term representing the quantity A exclusive OR B times C in. Simultaneously, input A and B are connected to a separate AND gate, generating the term A dot B. These two intermediate products are then combined through an OR gate to produce the final carry-out expression. Cout equal A dot B plus C in times A exclusive OR B. This implementation requires a total of 5 gates, 2 exclusive OR gate, 2 AND gate, and 1 OR gate, representing an optimized design that balances functionality with circuit complexity and propagation delay considerations. Decoder fundamentals. A decoder is a fundamental combinational logic circuit that performs co-conversion operation. It accepts an input line and generates a maximum of 2 to the power of n unit output line. The decoder primary function is to convert coded binary information as its input into more recognizable or non-coded format as its output. The circuit activates a specific output line that corresponds to the binary number represented by the input combination. But the critical characteristic of decoder operation is that only one output is active or in the high state for any given input code. The block diagram illustrates an input line labeled A0 through AN-1 entering the decoder, which then produces an output line labeled O0 through OM-1. Physical decoder integrated circuits such as those shown in the images are commonly implemented in dual inline package configuration for practical digital system application. Decoder applications. Decoders serve numerous essential functions in digital systems across various application domains. In traffic light control system, decoders interpret timing signal and activate the appropriate light sequence, red, yellow, or green based on predefined timing scheme, ensuring proper traffic flow management. Security system utilize decoders to interpret access code entered by user, comparing them against authorized code to grant or denied entry privilege. In motor control application, decoders translate control signal into specific commands that regulate motor speed and rotational direction. Additional applications include television remote control, where decoder interpret infrared signal code to execute user command, and 7-segment display, where decoder convert binary coded decimal input into appropriate segment activation pattern to display numeric digit. These diverse applications demonstrate the decoder versatility as a fundamental building block in digital system design. Encoder. An encoder is a combinational logic circuit that performs the inverse operation of a decoder. While a decoder converts a small number of inputs into a larger number of outputs, an encoder accomplishes the opposite transformation. The encoder accepts multiple input lines and produces a smaller number of output lines that represent a binary code corresponding to the active input. A fundamental operation principle is that only one input line should be active at any given time to ensure proper encoding. The comparison diagram illustrates this inverse relationship. A 3 to 8 decoder accepts 3 input bits and then generate 8 output lines, whereas an 8 to 3 encoder accepts 8 input bits and produce 3 output lines. This inverse functionality made encoder essential for converting multiple discrete signals into compact binary representation for efficient data transmission and processing in digital systems. Encoder application. Encoders serve critical functions across numerous industrial and automation applications. In automotive systems, encoder provide precise motion feedback by sensing wheel rotation speed for traction control, measuring engine shaft position for ignition timing, and monitoring various mechanical components requiring accurate position or velocity data. Elevator control system employ encoder to continuously monitor and regulate the position and speed of the elevator car. ensuring smooth acceleration, deceleration, and precise floor alignment for passenger safety and comfort. In conveyor system found in manufacturing and material handling facility, encoder track belt speed, rotational direction, and the precise position of object moving along the conveyor line. The diagram illustrates typical encoder implementation. The left shows a conveyor belt monitoring system with encoder and counter components, while the center and the right images demonstrate rotary encoder configuration used in motor control and elevator position sensing applications. That's all for Chapter C. Thank you.